Hello, my name is Sierd Vries and I work at Delft University of Technology. Today I will talk about predicting Aeolian sediment transport and dune development for the design of nature-based solutions or coastal engineering in general. I run a program in Delft that aims to create sustainable coastal landscapes. I study the physics of Aeolian sediment transport from an engineering perspective. I study coastal landscapes where Aeolian processes and engineering are both of key importance. And today I will be in the bottom right corner of the screen. This is an example of a coastal dune landscape where natural processes and human interventions are both important. This is a location close to Amsterdam, here in the Netherlands. The beach is widened artificially by dredging activities to create space for safety and recreation. And at the same time, notches are built in the dunes to accommodate important species habitats. These dunes developed over time due to natural processes and human interventions. And there are many examples of this where I come from. In fact, I am quite used to digging, dredging, and the installation of vast human-made coastal landscapes along the Dutch coast, where I work and where I live. But these activities are not only limited to the Dutch coast. I see interesting activities, for instance, at the Aquitaine coast in France, where there has been an influence of decades of measures to keep the dune profile controlled and stable. And currently there's lots of interesting work to remobilize this coast again. Work by the team in Bordeaux. Also in Sweden and in Belgium there are examples of systems where engineering and natural processes are of key importance when it comes to the development of beaches and dunes. And in my final example in this introduction, I have an example from the US, where at several places the coastal system is nourished with sediment, such as here in North Carolina. Again, engineering and natural processes of wind-driven sediment transport are of key importance at these locations. These processes develop over time and create new perspectives for coastal landscapes. The list goes on, and if I look at these examples, I see engineering. Engineering on relatively large scales in dynamic systems. Engineering that goes beyond mitigating damage. I come from the field of hydraulic engineering myself, where hazards and flooding are the most urgent problems and dikes and concretes are the most common solutions. I see engineering here to create favorable environments for society's needs on a day-to-day basis. In that sense, I believe in some form of engineerability of coastal landscapes. Engineerability, in Dutch there's actually a word for this. It's called maakbaarheid. I cannot really translate that into English. Engineerability of coastal landscapes. This means that for me, that a coastal landscape can be created, its development can be stimulated, and it can be managed. I made this a bold statement because I do not really insist on you agreeing with me. I'm merely pitching the idea. And with this idea of engineering ability, I think predictability is an essential element. Good prediction can convince people to make certain decisions, reduce uncertainties, and new challenges can be explored. And I believe that research informed dune models can provide a useful tool. And today I will present a deterministic approach to Aeolian transport modeling of dunes for coastal engineering. And well, the architects of many models is characterized by some sort of feedback loop. In the case of coastal landscapes, we may propose a conceptual feedback between sediment transport, morphology, and ecology. And these elements interact and all sorts of complex things happen in their interaction. And in the remainder of this presentation, I will use this feedback loop. Let's start somewhere. Let's start with describing sediment transport. Sediment transport happens mostly at the beach. Sediment is moved by wind towards the dunes. The amount of sediments can be defined as a flux. And predicting the exact amount of sediment transport is important for predicting the development of the morphology of the dune. Also, with measured morphology of the dune, you can estimate the amount of sediment transport that took place. An example of that is shown here, and the amount of sediment transport can be significant. Here there is a net accumulation of sediment in the dunes. Aeolian sediment transport causes dunes to grow, and at this place the dunes grows fast, up to 40 cubic meters per meter per year. And also, this growth is very predictable in time. It's very linear, constant over the better part of 4 decades. And this linear growth is observed at many places. Also, the Belgium measurements show linear growth of the dune systems. And at different locations, linear rates of dune growth was measured. And I think this is a miracle by itself, but it's also good news for predictability. But what determines the magnitude of this growth? If you look in the literature, Aeolian sediment transport generally consists of 2 driving principles. First, there is wind forcing, and second, there is the erodibility of the bed, or the availability of sediment. These 2 things are generally summarized in sediment transport formulae. For some value of wind shear, sediment transport can be estimated based on some additional knowledge on grain size, transport threshold, and some empirical constants. These are typical representatives for the erodibility of the bed, and I see many people using formulas like this. There's Bagnold, Kuriyama, Doug Sherman, Leo van Rijn, and more recently Glenn Stripstein. The concept of erodibility is, the details of that is quite poorly defined. So I made it bold, and I want to elaborate on erodibility. And doing that, I would like to give you some homework. If you go to the beach on a dry day, I challenge you to get down to the sediment surface, get down on your belly and apply shear to the sediment surface. You will likely see that a limited top layer can easily be mobilized by just blowing on the sand. But underneath, a more resistant layer seems to be present. These are 3 examples taken all over the world. I've been showing these videos for a while now, and people send me videos when they do these experiments themselves at many places. These examples show that erodibility seems to be time dependent. Zooming out a bit to a more realistic situation, it's quite typical to see big gradients in sediment transport. Places with large sediment transports and no sediment transports are close to each other. These variabilities can now be explained partly by wind forcing and erodibility. The third driving principle that is often overlooked in literature is advection, as sediment that is transported at one location needed to be mobilized at another location. And I'm presenting a deterministic model that uses these 3 principles to predict Aeolian sediment transport. And for the people that are used to hydrodynamic modeling and sediment transport, there are similarities between the 2. Especially the concept of mass conservation is very important to take into account with this type of modeling. To conceptualize the model, I will use the figure by Charlotte Uppus. In this figure, there is a layer of transport on top of a bed layer where sediment can be exchanged based on the principles of erodibility. Sediment goes from left to right. And I propose a discretization that divides the layer where the sediment transport takes place and the layer where the erodible sediment is available in the bed. Well, sediment transport is mostly a horizontal process. Erodibility is vertically implemented. And now I'm going to add some difficulties and some administration, so let's make some room for equations. To predict sediment transport, I predict the sediment concentration at each grid cell as a function of bed level change that is defined in the bed. And I made these unknown variables yellow in the advection equation. So the left-hand side of this equation deals with the horizontal advection of the sediment concentration, where US is the sediment speed that may vary in space and time. The right part of the equation deals with the sediment exchange with the bed. The bed level, ZB, changes if there's a concentration gradient in time or in space. And the bed level change can now be defined as a function of the transport capacity, which can be calculated as a function of wind speed through a Bagnall type sediment transport formulation. More wind means a higher transport capacity and means a tendency to erode, and vice versa. But sediment exchange can also be influenced by sediment erodibility, here defined by SE. And this, the right-hand side of the bottom equation accommodates supply-limited Aeolian sediment transport. And supply-limited Aeolian sediment transport can occur frequently. For instance, when it's very windy, but it rains at the same time. Or in the example where we are blowing on the beach, sand, by ourselves. So here we have our morphological feedback loop defined, except the role of ecology. I would like to elaborate on the way I'm used to deal with vegetation and ecology. This is work adopted from Orencio Duran and Laura Moore. They have made a lot of progress on the implementation of vegetation in dune models. Very nice work, and it inspired me a lot. They proposed on the level of every grid cell that the reduction of shear stress can be calculated as a function of vegetation density. This reduction stimulates deposition and limits erosion in the advection solver. Vegetation density is defined by ρ. And then this vegetation density is a value between 0 and 1, which is a function of the vegetation height normalized by some assumed maximum, which can depend on vegetation species. Then the vegetation can grow with some assumed growth speed, vertical growth speed. And this is an important assumption because the other way around, when we assume a growth speed, the vegetation height can be calculated, which influences the vegetation density, which determines the reduction of shear stress. So this is a dynamic coupling between the growth of vegetation and the reduction of shear stress. Let's take these principles and calculate Aeolian sediment transport using the advection solver. So let's have a domain here, a beach and dune system, and we apply a grid. And the grid represents the calculation points. Then we calculate Aeolian sediment transport, and we take into account the steering of the wind field. That means spatially varying wind shear, which can be accommodated in the advection solver. Then we have the fixation by vegetation, which influences the erodibility of the sediment. And again, we use the morphodynamic feedback loop. So at every grid point, we calculate sediment transport morphology and ecology in a spatial temporal arrangement. So let's apply this to a very complex system of 5 so-called notches. These notches are located in the Netherlands, and they are studied extensively by the group of Professor Gerben Rusink from Utrecht University. These notches are made to promote the sediment transport towards the hinterland, mainly for ecological reasons. And project goals of these notches projects span multiple decades, and the prediction on the development can be used to inform management. From the site looks like this. We have used topographic maps from this site and applied the morphodynamic feedback loop to calculate the development. I will jump to the results. Results show the development of this site during a period of 10 years, A time series of nearby winds, waves, and water levels are implemented, but also grain size properties and vegetation characteristics. We can see the sediments slowly creeping into the hinterland. And since we have data from this site, we can compare. The scale of this model is about 1 kilometer, and the modeling period is 10 years. The calculation time is in the order of a day. We see erosion in the blue in the necks of the notches, and we see sedimentation in red in the depositional lobes. The magnitude of sedimentation and erosion that are observed matches the magnitude that is modeled, which is very promising in my opinion. And this model can now be used to study case studies such as the Zandmotor, which is a bit bigger, with some success. And I would actually like to encourage to learn more while applying this model capability. I really believe that this can create new opportunities for managing dynamic coastlines. And with rising sea levels, I think we may convince people to use natural forces, Aeolian transport, dune building forces, instead of using concrete and stones. So coming back to the title of this talk, Aeolian transport modeling of dunes for coastal engineering. I try to provide a starting point, and I would state that the predictive skill for morphology and sediment transport is promising. And from that perspective, I would like to encourage the development of case studies. These case studies could be considered low-hanging fruits for applications and informing managers, but also I believe that these applications are essential for further knowledge development, as they will provide data for validation and further process development. Also, I see that the knowledge when it comes to modeling dunes is distributed over different disciplines, especially the link between models that deal with vegetation and morphology needs a bit more elaboration. Also, the definition of the ecological behavior parameters, vertical growth rates and vegetation density between 0 and 1, do not actually describe ecosystems yet. I'll finish acknowledging the people that helped advancing this work. I'm presenting today myself, but this story is really because of a group of people and also the institute that supported this. I think we are lucky that so many people are motivated to work on this, and I believe that we can make, well, we can engineer a bright future for our precious coasts. And I would very much like to welcome collaboration on this topic. We have shared all the application encodes in this position paper on numerical modeling of coastal dunes. And everything I've showed today, you can reproduce by yourself. We have published an open Python software library that can be found on GitHub. And we use it as a catalyst for our collaboration. So please join us if you're interested in collaborating on the modeling of coastal dunes. Thank you very much for listening, and I'm looking forward to your interaction.